Hello guys, welcome back to another video. Today we're going to be starting a 5-part series, and it's going to be centered around calculus. And the prerequisites for this series is that you've covered limits, or you have an idea what a limit is and how to solve one, especially for polynomial powered variables. Which shouldn't be too difficult, but if you haven't had any background with that, you should check out a video. But yeah, so we're going to start calculus. And so the main idea of calculus has to do with, or at least derivatives, has to do with slopes. And here we have a function x squared, f of x equals x squared, and we've only defined it for the positive numbers. And if we pick two random points, x and x plus h, we can find the slope between those 2 points. And we can do that by doing difference in y over difference in x. So our two y values are f of x plus h and f of x, and that's on top, and then that's divided by the x plus h minus x, so the difference in the x values. And so this is just the general formula, and we can simplify it a bit to get rid of the x's here. This is the general formula for finding the slope between 2 points. However, if we wanted to find the slope between 2 points that got closer and closer together, we would have something known as a derivative. And here we can use the concept of a limit to actually push that beyond 2 points that are close together to a tangential point. So a point that is tangent to the curve, meaning basically a point that doesn't intersect the curve at two distinct places, but only intersects it when you draw a line through it. It only intersects it at one point, right? So that's why we need this limit as h approaches 0, because we're really squeezing those 2 points into one. And when we solve this, we get a derivative of the function, and that is able to give us, for any x value that we choose, it's going to give us back the slope of the tangent point there. Okay, so for the function x squared, we can put this into this formula where the limit approaches 0, and what we get is x plus h squared minus x squared all over h. And that becomes, when you expand x plus h squared, that becomes x squared plus 2xh plus h squared minus x squared over h, and we can simplify this by cancelling this and that out, and we get h squared plus 2xh plus, all over h. Now, from the numerator, we can factor out an h, and when we do, we get h over h, which is just 1, so we actually just get h plus 2x. And we have a limit there. We have the limit as h approaches 0. So we can actually evaluate that limit and say that h is equal to 0. And that just gives us 2x. So that means, and this is called a derivative, so that means the derivative of the function x squared is 2x. And remember, what the derivative does is it gives you the slope at any point. So the slope at the point 3, 9, for example. So if you plug 3 into the function, you get an output of 9. But what if you wanted to know how the function is changing, what the slope, what the rate of change at the point 3 was? At the point 3, if we plug that into our derivative formula, we get 2 times 3, which is going to be 6. So at that point, for every minuscule change in x, y is changing 6 times. And you can see that that changes all throughout this function. This slope is variable. Like if you had a slope here, it would be different than if you had one here, if you had one there. It's different all throughout the function, and that's why it's a function itself. So the slope isn't a single value. The slope depends on the input value that you give it corresponding to your function, right? But this is just the derivative for x squared. What if we wanted to look at different functions, maybe x cubed, x to the 5th? What would the slope be then? So we can take the same idea to a function like x cubed, and if we repeat the same process as I've done here, we're going to get 3x squared as the derivative. This is the notation for that. We just put a dash next to our function. And so 3x cubed, and remember if we had x squared, that was 2x. So it seems like the power becomes the coefficient of x, so it kind of goes down. Right, but for x cubed, we didn't have just 3x, we had 3x squared. So the power is always going to be 1 less than the power that it was initially. So if we have a general theorem for that, for any number that you can think of, where it's a real number, if you have a function x raised to that power, the derivative is going to be that power times x raised to 1 less of that. So some examples are x squared becomes 2x, and x cubed becomes 3x squared, and x to the fourth becomes 4x cubed, x to the fifth would be 5x to the 4, and so the power becomes 1 less, and the coefficient gets multiplied by the previous power. So this still applies if you already have a coefficient there. So you might be thinking like, what if I have something like 6x squared or 6x cubed, whatever. We can bring that power down, and this will become 2 times 6x. So now this is 12x. So whatever the old coefficient is, you multiply it by the power and you subtract 1 from the power. And that's your derivative. So, and also if you don't have any power, so you just have x by itself, that's fine as well. Let's say we had like 5x is our function. We would have our derivative is just 5, because this 5x really is 5x to the 1, right? So if you subtract 1 from 1, you get 0. So x to the 0, or anything to the 0, is 1. So you just have, you can get rid of this and just say 5. And this makes sense because the slope of a straight line is constant. It's always going to be 5. There is no variation in slope if we draw the line 5x, the line 5x like that. The slope at any point here is going to be 5. Whereas if you had a function like x squared, you have different slopes throughout the function. So this is a really introductory lesson to derivatives, and it introduces the power rule, which is basically if you want to take the derivative of any function in the form of x to the n, x to some power, then you're going to get n times x to the n minus 1. And in the next videos, we're going to be focusing on what if your function doesn't really fit that criterion? What if it's not x raised to the n? What if it's like sine of x? Or it's sine of x divided by x squared? Something complicated like that, you can still take the derivative, still find the slope at any point, but you're going to have to use different rules. The power rule is not going to apply there. You're going to need probably the quotient or the product, which will be covered in the later parts of this series.